Okay, so welcome back to the second session this morning. So next talk is by Dongxue, talking about covariant loop quantum gravity in numerics, real complex critical point, and ongoing developments. Please.
Thanks for the introduction. Thank you all for being here today. It's my pleasure to get to spend some time with you. Thanks to Joe and Muxin, local FAU students, to organize such an amazing conference. And also thank you for offering me this opportunity to present my recent work. So this is a plan of today's talk. First, I will introduce the motivation of my work, and then provide some overview of spin forms, and move to the real and complex critical points. In this section, I will first introduce the numerical algorithm on how to construct the boundary data and obtain the critical point. Next, I will introduce how to compute the complex critical point. And in the last section, we will move on to some physical scenario, for example, the cosmology, and look at the cosmological dynamics from the framework with the scalar matter. So the motivation of my work, as we know, the spin form theory is a covariant approach of loop quantum gravity. And the spin form amplitude defines the transition amplitude of loop quantum gravity states. The main challenge has always been the difficulty of computing the spin form amplitude. However, recent years, the numerical progress on spin form models provides us a powerful tool to do the computation. For example, the SL2C form library based on the 15G symbol plus the boosters, and the spin form renormalization, the effective spin form model, and our previous work on computing the spin form propagator on the Lipschitz symbol by using the Monte Carlo method. And the other groups, they also use the Monte Carlo method to compute the spin form observables. So we also bring up and develop the method of complex critical point and the method of asymptotic expansion. Today, I will focus on the method of complex critical points, which is a generalized stationary phase approximation of spin form amplitude. We develop the scheme as following. First, I will introduce how to construct the boundary data, the algorithm, how to construct the boundary data and the real critical point. Next, we perform some deformation of the boundary data. Then we need to compute the complex critical points. So any candidates of quantum gravity should relate to general relativity in the semi-classical regime. In loop quantum gravity, according to the area spectrum, the classical area should be much greater than the Planck length square, which means the large G. So this motivates us to understand the large G regime as the semi-classical regime. And the semi-classical analysis of spin form amplitude have been extensively studied. Many people contribute to this area. One of the interesting things to use the complex critical point is to extract the properties of effective theory from the spin form amplitude in the large G regime. And recently, we have some new developments. We use the method of complex critical point to develop better understanding of the quantum cosmology from the spin form theory and investigate the effective dynamics of cosmology from the large G spin form amplitude. To help the audience better understand spin form, so this section, I will provide an overview of spin form. So this is the covariant path integral in quantum gravity. And we define the transition amplitude by using the covariant path integral, which is given by summing over the history of three geometries. And you can see this is a 4D manifold with the 3D boundary slice. And this is the initial boundary slice. This is the final boundary slice. The history of the three geometry is given by summing over the 4D metric. We adapt this framework to loop quantum gravity. And we know in loop quantum gravity, the 3 geometry is quantized to quantum 3 geometry by using the spin network states, which is described by 3 types of data. First is the gamma graph, and with number of nodes and links. Secondly, there are number of spins to color the links. And thirdly, there are number of intertwiners to color the nodes. More precisely, the spins are irreducible representation of SU2, and the intertwiners are the invariant product of the representation space. And in spin form, we also define the Hilbert space on the graph. So the physical picture of the 3 geometry is that the spin network states describes the quanta of the 3 geometry. More precisely, we use the nodes to carry the quantum polyhedron with the quantum number intertwiners, and the links carry the quanta of the area with the quantum number spins. So now we know the path integral is given by summing over the 3 geometry. And here the 3 geometry is the spin network. So what we need to do is only to sum over all the spin networks, the history of the spin network. This gives us spin form. In other words, spin form is the histories of spin networks. And this is a spin form with some spin networks on the boundary. So the spin form phase is the evolution of the spin network spins or the links on the boundary, and the spin form edge is the evolution of the spin network nodes. The intersection of the spin form phase gives us the vertex. So then we can compute the spin form amplitude, which depends on the 2 complex and the boundary 3 geometries. I will introduce the 2 complex later. In other words, the spin form amplitude, you can consider it as a map from the 2 complex and the boundary 3 geometries to a complex number. So we construct the spin form amplitude to study the quantum dynamics in loop quantum gravity. And you can consider we discrete the whole space-time into a lot of the elementary building block. And we use 4 simplex to describe this elementary building block. When we glue 2 4 simplices together, you have the shared common tetrahedron. And these are the boundary. This one is the bulk. So when we compute the spin form amplitude, it's very similar to the general path integral formulation. You have the initial state, final state, and you separate it into small time pieces, and then you compute the small amplitude. Similarly, when we compute the spin form amplitude, we just separate the whole space-time into small regions. And between these regions, we have the shared tetrahedron, and this shared tetrahedron can be replaced by the resolution identity. And now let's give some formal definition of the spin form. So the spin form will depend on 3 types of data. Firstly is the 2 complex. And the 2 complex will include a lot of oriented faces, oriented edges, and vertices. So these 3 types of data will give us the 2 complex. For each oriented face, it will be associated with SU2 spins. Each oriented edge is associated with the SU2 intertwiner. And for each vertex, we can compute the vertex amplitude, which will depend on the spin and the intertwiner. So with the vertex amplitude, we can compute the spin form amplitude with more vertices. It's very like computing the Feynman diagram. You just put all the vertices together and make the product with respect to all the vertices. In the end, sum over all the spins and the intertwiners with some weights. And here, the vertex amplitude is the trace of the intertwiner. So recall that we define the SU2 intertwiner in spin form. However, here, this intertwiner is not SU2 intertwiner. It's the SL2C intertwiner. And this SL2C intertwiner will be determined by the SU2 intertwiner. And here, the determination from the SU2 intertwiner to the SL2C intertwiner, we use the Y map. And the Y map is just a map from the SU2 unitary ERAP to the SL2C unitary ERAP. And this is the this SL2C unitary ERAP with two labels. One is rho, which is the continuous label, taking the real number. And the K is the discrete label, taking the half integers. And here we let rho equal to gamma times spins, K just equal to spins. And this is the formal, the concrete formula for the Y map. So to construct the SL2C intertwiner, we first apply this Y map to the SU2 intertwiner. And then we apply this invariant projector to this SL2C invariant tensor space. We got the SL2C intertwiner. And then we plug this SL2C intertwiner into the vertex amplitude. We got the so-called EPRL vertex amplitude. And with this EPRL vertex amplitude, we just use the previous mechanism. We put all the vertices together and mix the product, sum over all the spins and the intertwiners. We got the EPRL spinfold amplitude. And here, actually, this EPRL spinfold amplitude has a lot of nice properties. One of them is this part. It's finite by removing the SL2C gauge redundancy. And this spinfold amplitude, actually, we can rewrite it with this path integral formulation with the spinfold action. It's almost straightforward, just the sum over all the vertex actions. And the vertex action is the sum over the half-edge action. And we can use either equation 1 or equation 2 to compute the half-edge action. It depends on the type of the phases, to be the space-like phase or the time-like phase. Here we covered both EPRL spinfold model and the Nebida-Karady extension model, because then we can look at more physical scenarios like cosmology and the black hole. So with this, we have the boundary data, which is spins related to the phase areas. And we also have the SU2 or SU11 spinners, which relate to the phase normal to each phase in the tetrahedron. And the integrated variables include the SL2C group element, spinner, and may include this SU11 spinners. The path integral formulation of the spinfold amplitude is very important to the semi-classical analysis, because then we can apply the stationary phase approximation. And for the stationary phase approximation, it's crucial to compute the critical point. So in this section, I will introduce how to construct the boundary data and compute the critical point. We already have a very concrete mathematical package and posted on the GitHub. So if you are interested in, just download and look at it. So the idea is, I will use the vertex amplitude as an example to introduce what is the real critical point. So when we probe the large J regime, we will scale the spins by a large number lambda. And in the end, the action will be also scaled. So then we can apply the stationary phase approximation to the action, and the solution to the critical equation gives us the critical point. The early stage of the stationary phase analysis of spinform primarily focus on how to classify the critical point and how to reconstruct the discrete geometry from these critical points. However, when we do the calculation, we compute the spinform amplitude, we figure out actually we have the semi-classical geometry first. And we need to use this semi-classical geometry to construct the critical point. It means the reverse procedure. You have the discrete geometry, and from this discrete geometry to construct the boundary data and get the critical points turns out to be more practical to the calculation of the spinform amplitude. So then I will introduce how to construct the boundary data and the critical point from the geometry. And the geometry is given here by the 4D coordinates in the Minkowski space. And this is an example of the coordinates. So with these coordinates, we can decide the type of the edges. And with these edge vectors, we can compute the 4D normals. And then with the 4D normals, we can get the dihedral angles. The critical point, we can compute the critical point from the geometrical interpolation. So we know the SO13 group element actually it relates to Lorentzian transformation. And gluing all the tetrahedron together to form a full simplex. So then we can have the SO13 group element. Then we can lift this LO13 group element to SL2C group element, gives us the critical point. So now we move to the tetrahedron, look at each face. It's easy to compute the triangle areas. And here, actually, this SU2 and SU11 spinors, they are related to the face normals to each face. And because the spinform space is oriented, so we need to decide a consistent orientation. After that, with the boundary data and the critical point of SL2C, we can compute the Z which belongs to CP1 up to a complex scaling. So by now, from the full simplex geometry, we construct the boundary data and the critical point. After removing the continuous gauge freedom and do the real parametrization, actually in the end, the full simplex section is just a function with 44 real variables. And we can evaluate the action at the real critical point. You can see this is the action's number, and the real part of the action at the real critical point is 0. Furthermore, we can check the equation motion, which is satisfied. Okay, so now let's generalize this algorithm to all the simplicial complex. And I use these two full simplices as an example. So what we need to do, just if we are given the coordinates, just repeat the previous procedure and compute the boundary data and the critical point separately. Then glue them together just to make sure the face shared by these two full simplices, they have matched the face normal. So once we do this, and after the gauge fixing, we got the boundary data and the critical point on the simplicial complex. And then we do the real parametrization. We got the spinform action. And here for this example, it's just a function with 91 real variables. And we can evaluate the spinform action on the critical point for this example, and furthermore check the equation motion, which is also satisfied. So I want to see actually this algorithm can be generalized to any simplicial complex, and we can construct the boundary data and obtain the critical point. So for example, the delta 3 triangulation with 3 full simplices, and the double delta 3 triangulation with 6 full simplices, and the hypercube triangulation with 24 full simplices. And the even more complicated one, we use it to construct the double hypercube full simplices. Okay, so now let's move to how to compute complex critical point and its applications. So when people generalize the stationary phase approximation to the simplicial complex, there was a confusion that the EPR spinform seems to be dominated only by the flat Regge geometry. This is because the derivative of the action with respect to spins equal to 0. This gives us the deficit angle equal to 0, or modulus the 4 pi times integers over gamma. To resolve this flatness problem, we introduce the method of complex critical point. And let us consider the large lambda integral. Here is the integral, and this action is analytic function. And the R is the external data, x are real variables. And the U cross K is the compact neighborhood of R0 and X0. Here, X0 is the real critical point. Then we can do the analytic extension to both the variable and the action. So the solution to the complex critical equations gives us the complex critical points. Let me use this graph to illustrate the relation between the real critical point and the complex critical point. So if R, the external data, is equal to R0, then we have the real critical point. Then we deform R from R0. This real critical point will move smoothly from the real axis to the complex plane. Then we got the complex critical point. With the complex critical point, now we can compute the large lambda asymptotic expansion. Look at the left-hand side, it's the integration with the real domain. But the right-hand side is the asymptotic expansion at the complex critical point. And this inequality tells us only the imaginary part of the complex critical point equal to 0. The real part of the action will be 0. And the other case, if the imaginary part of the complex critical point not equal to 0, then the real part of the action will be always less than 0. So this gives us the interpolation between two regimes. The first regime, if R equal to R0, then the real part of the action at the complex critical point will be equal to 0. So this gives us the oscillatory phase. But if the R not equal to R0, the real part of the action will be less than 0. So this amplitude will be exponentially decay. It gives us a smooth description of the asymptotics in the parameter space of R. And for any given lambda, we can always find a small imaginary part of the complex critical point, which the real part of the action is not small. And for any, so our code can also compute the complex critical point in the neighborhood of the real critical point, as long as the input is the real critical point. We can always find the complex critical point in the neighborhood of this real critical point. And evaluate the action at this complex critical point. You can see the real part of the action is less than 0. So actually, this method can help us resolve a lot of confusions. And the first example, I will use this for simplex. So for the boundary data, R is equal to R0. Here, R0 means the Lorentzian Regge geometry. And the tetrahedron, they are glued with the ship matching. Then in this case, there are two solutions with two oscillatory phases in the asymptotics. This is the asymptotics of the full simplex amplitude. And if R is not equal to R0, corresponds, we don't have the Lorentzian Regge geometry, then there is no solution. So people think, okay, then the vertex amplitude will be exponentially spread. But actually not, because if we introduce this delta Z4, which donates the deviation from the ship matching, if this delta Z4 not equal to 0, it means the tetrahedron, they are glued with only the area matching, but not the ship matching. You can see we can always find some small deformation, which the amplitude is not small. So this is the first example. And the second example, I will use the the delta 3 triangulations to resolve the flatness problem. The flatness problem tells us for the boundary data correspond to a flat Regge geometry, then there is a real critical point, and the amplitude gives us the oscillatory phase. But if the boundary data corresponds to a curved Regge geometry, then there is no real critical point. In this case, the amplitude will be exponentially suppressed. But if we use the real critical point to represent the flat geometry, and use the complex critical points to represent the curved geometry, you can see the amplitude for these curved geometries actually is comparable to the amplitude of the flat geometry. So it means the flatness problem is resolved by using the method of complex critical point. The last example here, because delta 3 triangulation doesn't have internal edge, so the Regge dynamics is trivial. We want to look at the Regge dynamics. So we construct this double delta 3 model, just glue two delta 3 model together. And there is an internal edge. So this internal edge gives us the non-trivial Regge dynamics. And here, instead of looking at the full amplitude, we split out one spins to look at this curly z, which we called it partial amplitude. And this partial amplitude will be gives us the effective theory. And here, this action is the effective action, which depends on the splitting spin. And because we want to look at the Regge dynamics, we change the variable from the spin in spin form to the internal edge. And now the full amplitude actually is the integration of the internal edge. And then we can compare the spin form with the Regge dynamics. And this is the result. You can see the Regge dynamics is almost reproduced for small gamma and gets some corrections for the finite gamma. Okay, so now I think we already know more than enough of the complex critical points and the applications. Let's go to some physical scenarios in cosmology. Let's look at the cosmological dynamics from the framework of spin form with some scalar matters. So I think hypercube is the best model to study the homogeneous and the isotropic quantum cosmology. So then we choose the hypercube complex, and then because we want to apply spin form, then we triangulate the hypercube into 24 full simplices. We also do the periodic boundary condition. In this case, along the time direction, there are two cubes. If these two cubes have same edge length, then we have the flat geometry. But if we let the edge lengths are not equal, actually we create curved geometries. And because it's crucial to couple the matters in cosmology, so here we will couple this kind of scalar matter to the spin form action. And on the boundary, we also use the coherent state for both the spin form and the matter. So here, actually, we introduced some external data, which relies on the geometry, the extrinsic curvature, and the phi pi. They are the canonical conjugate variables of matter on the boundary. So here, the spin form amplitude coupled with the scalar matter, we got the effective action. We call it effective total action. It's the sum of the spin form action with the scalar matter action. And here, the integrated variables actually is around like 1,200 real variables. And then we can compute the complex critical point. But before we compute the complex critical point, we need to construct or get the real critical point. We just set a flat geometry and make the boundary vacuum. Then, from this real critical point, we make some deformation. We let the initial slice, the initial data satisfy the Friedman equation. And this is the Friedman equation. And for the final slice, we impose some data, this pair of the final data. And each final data, we can always find the numerical solution to the critical equations and get the complex critical point. And then, actually, this from the earlier idea on the spin form cosmology. Actually, the maximum of the spin form amplitude always corresponds to the Hamiltonian constraint, which gives us the modified Friedman equation. And here, the real part of the total action at the complex critical point, the maximum value, is also the maximum value of the spin form amplitude. So we need to figure out the corresponding K critical for each fixed phi f and pi f. Then, for each fixed phi, we will running this pi f and find out the relation between this k critical and the pi. In the end, the numerical result tells us the constraint equation is like this. And let's compare it with the classical freedom equation. So you can see we get an effective scalar density, which includes the pi square term and also the higher derivative terms. So here, this phi naught alpha 0 is a constant term. You can understand it as the effective scalar potential. And because this constant term is greater than 0, so it can place a rho similar to an effective positive cosmological constant. And because this constant is not equal to 0, so it indicates that on the final slice, the extrinsic curvature is greater than the extrinsic curvature on the initial slice, which means there is a accelerating expansion for the universe. Okay, so let's move on to a more complicated case. This is the last example. We glue two full-simply hypercube together. Then along the time direction, there is a common cube. And if these three edges, cube's edges are same, then we get the flat geometry. But if we let the inner one, the inner cube has a less edge length, actually we get a curved geometry. And then in this case, we also triangulate it into 48 full-simplices. We make an analog of the symmetric bonds. And here we also impose some conditions for the initial and the final slice. This is the condition. Sorry. So we impose these conditions, and we got the conditions for the initial and the final slice. We also have this condition. The initial slice extrinsic curvature is less than 0, and the final slice greater than 0. So it means we create a constructing and expanding universe at the initial and the final slice. And here, A naught will be evolved from the negative to positive, which means a bounce occurring in the evolution. So with these conditions, we do the similar numerical simulation and get the similar result. The relation between the k critical and square and the pi also satisfy this constraint equation. So this also gives us the modified freedom equation. And when this symmetric bounce happens, and the effective scalar density, which contains a higher derivative, is pi to the cube and pi to the fourth. And the scalar potential vanished. You can see the constant term vanishes because the scalar potential, we can consider the scalar potential vanishes because there is no constant term. So in the end, this is the conclusion. We have the numerical method of real kind of complex critical point, which provides us a powerful tool to study the spin-form amplitude. And our work also provides a general procedure to numerically construct the boundary data and compute the critical point. And for the case, like the real critical point is absent, we have the method of complex critical point. And we can use the complex critical point method to study most physical scenarios like quantum cosmology, and the coupling of the scalar method to the spin form yields non-trivial physical implication for the effective cosmological dynamics. And in the end, actually, the similar study has been carried out to the black hole to white hole transitions, and I think Cong will introduce it on Tuesday. So next is the outlook, and I will divide it into two parts, the numerical algorithm and the physical application. For the numerical algorithm, actually we also have the algorithm of computing the next two leading order stationary phase approximation. And in the afternoon, I think Haida will present it. And we also want to compare our result to the result of SL2C form library on the 15G symbol plus boosters. And maybe we can use the Lifshitz symbol from the complex critical point to compute the spin-form propagator on the curved geometry. And the physical application, because now I only use 2 hypercubes along the time direction. Maybe we can generalize to more hypercubes and to see more accurate representation of the cosmology. Or actually, we can also develop techniques to fit in the higher dimensional parameter space. In the end, maybe we can also compare our result from the spin-form cosmology to the loop quantum cosmology. Okay, thank you.
Thanks, Dongxue, for nice talk. And we have 5 minutes for questions.
Hi, thanks for the talk. Why is the large J regime the relevant one in the bulk? I mean, in the boundary states, you can choose whatever you like, but in the bulk, why is that the relevant regime?
You mean which model?
Large J.
Large J?
Why are you interested in the large J regime of the spin-form amplitude in that bulk region? In particular, when in the region you would then associate with the bounds.
Yes. Here I introduced the large regime because we always want to compare the large regime because it corresponds to the semi-classical regime. We want to compare the result in the semi-classical regime. But yes, so that's the motivation of the comparison.
Yeah, but what would you expect that regime to be, that region to be semi-classical? Even assuming that large J means semi-classical.
Even we look at the region for the bounds, it's also semi-classical region. So because we proceed the semi-classical analysis to the bounds, so even this part is also the semi-classical regime.
Is it a result, or you're assuming it's semi-classical so that you can use the large J approximation?
So we assume this because we create these conditions.
But then the statement would be that the quantum bounds happens in a semi-classical approximation to the dynamics, which I find strange. I mean, maybe it's true, but it's a bit strange.
Because here you can see the edge length is smaller than the boundaries, so we think it is a candle bounce. That's the framework.
Maybe I have a comment on that. So here, the approximation, the regime we are looking at is only the large J regime on the boundary. And the bulk large J approximation is a change of variable. It's emerged automatically. And here, I wouldn't say this is semi-classical. It depends on, of course, what you mean by semi-classical. So this is effective dynamics. So this is the effective dynamics derived from spin-form. Next question.
Hi, Dongxue. Thank you very much for the very nice talk. My question is on the application of this complex critical point methods to the time-like amplitude of the Conrad-Inebide extension of the EPRL model. Because it is known from the literature that the time-like amplitude is particularly idiosyncratic in that the critical point equations, the equations that determine the real critical points, so stationarity and maximization of the real part of the action, do not uniquely characterize isolated critical points. So there's a critical line of real critical points.
So here we just choose one of the critical point. So you can see for the time-like equations. So we have 2 edge. You can see, it's very, okay. But if you remember on the slides, we have the half edge action. And for the time-like tetrahedron, we choose one of the critical point. So then we can always find one with a critical point.
So my question in particular was that if indeed it is true that the critical point equations do not determine isolated real critical points, the asymptotic theorem of Hormander's, which is what underlines the, as far as I understand, the complex critical point construction, may not be applicable. So it may not be that the time-like amplitude, the integral that you look at, can be written as the exponential of the action evaluated at this line of critical points times this measure factor evaluated at the real line of critical points.
Of course.
So then if this is not the case, meaning if the asymptotics of the time-like amplitude is not really completely under control, how is it that the complex critical point method can be applied, in particular for this very nice application to cosmology that you've mentioned in the last part of your talk, where you really need to have time-like amplitudes?
Actually, here it didn't compute the amplitude. We just like evaluate the action at the complex critical point. But actually, we can just put the critical point into the measure, and maybe we can look at actually here we can only look at the first leading order. But of course, you can look at the next leading orders.
And then on that point,
we can.
Just a very quick follow-up question. Is it clear then that as you explore the configuration space of the boundary, that the maxima of the action are indeed the maxima of the amplitude? Can it not be that this measure factor, which we do not have good control over, behaves in such a way that that it can change? Since it's a multiplicative factor to the exponential, why is it clear that the maxima of the exponential are indeed the maxima of the amplitude?
Also, actually here, I think the maximum of the spin-form amplitude, it is, we can just look at the maximum of the spin-form action at the complex critical point. So we can just ignore the measures. So they are equivalent.
The last one quick question. Yeah,
okay, I can just follow up a little bit on Daniela's question. Quick question. Mushin, you clarified something, but then at the end, is it the case that the bounce is happening at low densities, low curvature? Because of you said you can make a transformation, so there is still large J's and so on. So is the bounce happening at low matter density and low curvature?
Yeah, very good. So we have discussed a lot of time about it. Yeah, so right now I'm not 100% clear about it. So yes, maybe not. So because this is complex critical point, and inside there's no geometrical interpretation. So there's only geometrical interpretation on the boundary. So what something makes sense is to, for example, comparing the action, the complex action, to, for example, mu-bar scheme and this. Yeah, so this is something.
To me, it seems a little bit like limitations of the mu-zero scheme, where also the bounce could happen with the density of water.
Yeah. I agree with that. Yeah. Maybe Carl.
Just a comment on that. From the loop quantum cosmology side, one does expect that the bounce happen at large J. So
But if you have a closed universe let's focus on a closed universe so that we can picture it. The bounce happens at the sides that is many order of magnitude larger than the Planck length. This is your result with van der Slot. So, I mean, here a large universe means J larger than 3, 4, 5, and so on. So in this sense...
No, but it's large, but I mean, the statement is really what is the density? Even in that case, the density is still high at the bounce, right? I mean, doesn't happen at the density of water, because if it happened at the density of water or even at density of nuclear matter or something, then one would say that, well, I mean, so that I think is a critical thing to check.
Yeah.
Yes, I agree. So that's the thing we need to check furthermore.
Mushin, I had a question.
Sorry, I think we have to really stop. So the next speaker is waiting, so we have to really stop. So we can ask questions after that.
Sorry about that.
Let's thank Dongxue again for the talk.